Good morning. Today we are finishing up with yesterday's objective, CO75. Yesterday we were working on rolling the dice 20 times, 120 times. So we rolled our dice 120 times and we just logged in everybody's amounts that they rolled of each number 1 through 6. Now we've been working on adding up how many ones were rolled by the whole class of 21 students, how many twos, how many threes, how many fours, fives, and sixes. So how many ones did the class roll? 450? How many twos did the class roll? 390. How many threes did our class roll? 392. How many fours did our class roll? 374. How many fives did we roll? 416. And how many sixes? 442. Okay, so if we remember, we were saying our experimental probability is it going to match our theoretical probability of rolling 420? So let's look. Making sure, we don't have anybody else. Okay, so 450 is a little bit more, 390 is less, 442 is more, 416 is really close. So if we look at our personal rolls, so each person was trying to get 20. We had one person actually get 20 for every roll. There's a number of people that had 20 for individual numbers. So some of us actually got that theoretical roll, but their other rolls didn't quite match. So what we want to do is we want to see which one got closer to the theoretical probability. If we were rolling just by ourselves, or if we were rolling as a whole class. Do you have a question, Jillian?
So it said if you each roll the dice 120 times, how many rolls would that be? I put 2,520, but I added it up and I got 2,464.
2,464? 2,464. So why do you think our actual rolls might be less than what we were supposed to roll?
Oh, because it's theoretical.
James?
Well, whoever did the 2016 12, 12 and 15, 27, that only equals 102.
Yeah. So some of us didn't actually roll all the way to 120. We got confused when we were rolling, and we didn't, because 120 is a lot. So as we were rolling, we messed up with our rolls. We messed up how many times. That does happen when we do experiments. We call that like user error, that we didn't count correctly. So you're right. Our numbers are going to be skewed a little because we didn't actually roll 2,520 rolls. Some people got messed up and our final count is less than what it should have been. So we might not really see what we're specifically supposed to be seeing in this. We're going to check and see. So what we're going to do is I want you to look at how many did you roll? Like I had 17, 15, 19, 25, 16, and 27. What I'm going to do is I'm going to see what that probability was. Did I reach the theoretical probability? My experimental is it the same as the theoretical? So you're going to check yours. How would we do that? How would we check if we reach that probability, James? So we're not going to multiply by 20.
Is it 17?
Remember, we make those fractions.
Yeah,
so I had 17 out of 120, right? 15 out of 120, 19 out of 120, 25 out of 120, 16 out of 120, and 27 out of 120. So what we were saying was we were going to have 20 out of 120. So 20 divided by 120 is 17%. So we want to see how close we were to 17% for all of our individual roles. So 17, I'm gonna do my own, you do yours, and see what percentages you got.
Do 17 divided.
You do your numbers. My number was 17 here. So I did, remember that fraction bar means divide. So take how many you rolled, divide it by 120. Yes.
My bad. It's actually 445. We miscounted.
Thank you. That brings us back to closer to a total. Thank you for double checking that. Once you get done with that top, we're gonna divide it by our 2,520. And we need to see what percentages we had there. Did we have close to 17%? I can see by my totals, I had 14%, 13%. 16% is really close. 21% is pretty high. 13% is low. 23% is a lot higher. So now I'm gonna see what it was for our class. Make sure you're working on your rounding. When I did my probabilities for the for the whole class, I got 18%, 15%, 16%, 15%, 17%, 18%. Are those numbers close to 17%? Yeah. When I did my own personal ones, I had really lows and really highs. So it was spread out more when it was just my 120 rolling. But when I looked at 2,520 rolls as the whole class, we are a lot closer to that theoretical probability. Why do you think that is? Why do you think as a class we got close to it, but me personally, I had some that were way off either on the top or the bottom? JT?
Because the other numbers that are not your numbers will like even out.
Yeah, because other people's rolls evened out my rolls. If I was high in the sixes, but I was low in the twos, somebody else was low in the sixes and high in the twos. And it balances out. The more rolls that we have, the more it balances out and the closer we get to that theoretical probability. Is that kind of making sense? The more you do something, the closer to the theoretical we get. That is our law of large numbers. When I did my own personal, I had really big highs and lows. But when we added all the class together, we evened each other out. So we got a lot closer to that theoretical probability. So we can see how our percentages bounce around that 17, 15, 16, 17, 18. So we're close to that 17% theoretical probability. My own personal, it was spread out more. So our law of large numbers is the more times you do something, the closer the experimental probability gets to the theoretical probability. The reason we do this is to really show that law of large numbers. To show how when we do it individually, you personally might have gotten lucky. And you might have gotten 20, 20, 20, 20, 20, 20. Most of us have probabilities that ranged farther away. So we had those highs and lows. The majority of us had highs and lows. Matthew was lucky and really got those 20s. He's the only one. Everybody else was bouncing around. We had somebody get 11 for one number. Okay, that's bouncing it around. Luciana.
On the test, are we going to have like a game like this?
No. On the test, we're not going to have a game. You're going to have to understand the experimental probability versus the theoretical probability.
Is it going to show it? Done, and then you have to figure out.
I'm not entirely sure. Okay, so I'll let you know when it gets closer to the test time. But you need to know that theoretical probability is what should happen. You should roll each number 20 times. But understand that experimental probability is what you're actually doing. That's actually doing the rolling, and it's not normally going to be exactly what the theoretical probability is. Then you need to understand that law of large numbers. That's why we added the whole class together. So we could see that, hey, my numbers maybe some of them were really off from that theoretical probability. But as a class, our percentages were bouncing right around that theoretical probability. So one way to think about when this would come in handy, Mateo is 19, and he is itching to go to a casino because he plays poker with his buddies in his dorm room. He's like, I want to go to the casino and see how I do. So think about going to a casino. You go in, you play a couple of rounds, and you win. That's exciting. What do you think is going to happen the more you play?
You're going to keep putting in more money into doing it, but then the more you put in, you could leave and lose all your money.
Probability-wise, what do you think the theoretical probability would be for the patron, for the customer in the casino? Are you more likely to win or less likely? Matthew?
The whole class is less likely.
So the casino is more likely to win. The customer is less likely. So if you go in and you get on a winning streak and you win a few,
I'm gonna want to play more.
what do you think you should do?
Stop.
Why should you stop, Aiden?
Because you don't want to lose. Because let's say you have good luck, but then you enter a lot of money because you have good luck, and then you just like.
Because what is probability telling us? That law of large numbers is telling us what? The more times you play, the less likely you will be to win.
No, but it's like.
Because the casinos are set up for the casinos to be more likely to win. So if you go in and you have a lucky streak, the more times you play, the more it's going to balance out and you're going to lose your money. Okay, so you always have to think, don't be greedy thinking, oh, I'm on a lucky streak, I'm going to keep winning. Because the more times you play, the less likely you are to win.
And then you get addicted to it.
And then you could get addicted to it, yes. But always remember, casinos are designed for the casinos to win more times.
It's still.
So the more times you play, law of large numbers, the less likely you will be to win. So will you have lucky streaks? Sure. Some of us got 26, 27 when we're rolling those dice. Ooh, that's awesome. Look, I'm getting all these sixes. I'm getting all these sixes. Uh-oh. Now I'm getting all these other numbers and I'm not getting those numbers. So law of large numbers, the more times you do it, the closer to that theoretical probability. And always remember, theoretical probability, casinos are more likely to win. There are other times you would apply this in your life. Gambling is a big one. Know what the probability is. If it is less likely for you to come out on top, law of large numbers, more times you do it, less likely you are to win. Enzo.
Like, if you win, like, a bunch of money, like, you made, like, say you won, like, $500 more than what you paid for it. In your mind, you're gonna think, like, you're gonna win more.
Right. In your mind, you get excited and you want to keep winning, but the odds are against you. Probability says you will not keep winning. All right, I need you to do that bottom part. Write out the definitions or the formula for the counting principle, probability, compound probability, theoretical and experimental probability. For my friends at home, we hope you are well and we hope to see you soon. Have a wonderful day.